Well, thank you very much for the introduction, Jim, and thank you for organizing this as well. I'm very glad to be presenting my PhD work on liquid solid flows. And I know that we have this wide audience, so I'm gonna start giving a little background into multi-phase flows and why we should study them before introducing the two projects that I worked for my dissertation, one in turbulent pipe and the other in liquid solid fluidization. So multi-phase flows refer to any combination of liquid, gases, or solids flowing together. Examples in nature include the flow of lava in volcanic eruptions, which is a solid in a liquid, and in staples in our daily lives, for example, orange juice, when it has pulp, is a case of a solid in a liquid. In industry, the processing of biomass, either in dry or in wet, present a solid flowing either in a gas or a liquid. And we can wonder, why should we study multi-phase flows? And I'll give you three examples. In nature, the study of mist in the atmosphere, a liquid in a gas, is of interest for climatologists to describe general circulation models, to make weather predictions, so that we know where to stay home in a snowstorm in the Midwest, or when to evacuate for a hurricane. In medical applications for aerosol therapy, another liquid in a gas, physicians are interested in knowing precisely the flow rate and the droplets size to deliver the optimal amount of drugs into the lungs. And in industry, for example, the pressure drop developed in a two-phase flows as a function of the Reynolds numbers detects the size of the pumps that we need for transport. And these are just examples in a vast number of applications. Basically, whenever we have heat, mass, or reaction processes happening in a fluid in motion, we need to know the fluid mechanics because these processes are coupled. And we can ask ourselves, well, how different are multi-phase flows from single phase? And it turns out that the presence of the secondary phase can have tremendous implications in the behavior of the flow, ranging from modifications to the mass and heat transfer coefficients, augmentation or reduction of turbulence in a process called turbulence modulation, and also changes in rheology. And I think that Paul is going to touch on that in his talk. So now that I've showed you why it's important to study these flows, I'd like to show you the work that I did for my PhD in two configurations. One was in liquid solid turbulent flows, and the other one in liquid fluidized beds. The video of the turbulent flow might look like it's a very slow flow, but it was taken at 1,000 frames per second. And so the real time for this video is actually like 0.5 seconds. So in real time, if you blinked, you would miss it. So now that it's playing a very, very slow, you can see the movement of the particles. And that research I did in Gainesville at the University of Florida. The liquid fluidization work was done at Irstea Laboratories in France, in the laboratory of Professor Pierre Philippe, and this was thanks to the NSF PIRE funding. So let's begin with the turbulent flow. Turbulent two-phase flows are present in many industrial applications, ranging from transport like from petrochemicals, minerals and ores, biofuels processing, wastewater treatment, just to mention some. And although they are so widespread, there's still a lot that we don't know about them. And that is important because a better understanding can help in many aspects. One of these is knowing when particles are going to settle, which can reduce problems with block lines that represent money and time expenses in industry due to shutdowns and repairs. Knowing more about the flows can help in the design of the new equipment, and also better simulation tools can help establish optimum operating conditions for current and future lines by maximizing solids loadings. In fact, according to a study by the Electricity Power Research Institute, an increase in pump efficiency can save thousands of kilowatt hours and dollars in water treatment plants dealing with 100 million gallons per day. So that's a lot of money. And one of the roadblocks for multi-phase flow understanding is the lack of experimental data. What I'm presenting in these plots are data sets, experimental data sets from the Journal of Fluid Mechanics as a function of the concentration, the solid volume fraction, and the Stokes numbers. The Stokes number is telling us how the particles is responding to the fluid. At very low Stokes number, the momentum of the fluid dominates, and the particles follow the fluctuations of the fluid precisely. This is the viscous dominated regime, and it will most likely be the case of flows with small particles or very viscous fluids. On the other extreme, at high Stokes numbers, the particle momentum dominates and the particle do not follow the fluctuations of the fluid. This is the inertia-dominated regime, and this will most likely be the case of flows of large particles or very low viscous fluids. In the middle, we have an intermediate regime where the particle kind of feel the fluctuations but do not follow precisely. And now that we know what the Stokes number is telling us, let's take a look at these available data sets. And I want to point out this region where there is no data, especially above 0.5% volume. Industries routinely operate at concentrations above 10%. So there is this large region where we need more information. And this lack of data has been identified as a roadblock for the progress of models. And obtaining data in this region was the objective of this study. And what is this data that I'm talking about? Well, if we take a look at the Navier-Stokes equation, which is the momentum balance on the fluid, we know that we have velocities and pressures. Now, in turbulent flow, however, these velocities are not only changing in space, but only in time. If we were to put a probe into a turbulent flow, what we would see is a velocity that looks like this graph here. We can describe this flow by using a mean and a fluctuation term, the Reynolds decomposition, and we can introduce this equation into the Navier-Stokes. And after, I would say, 3 pages of derivation and manipulating these equations, what we come up is an expression that is very similar, with the mean velocity in place where the original velocity was. And they are very similar, but they're not the same, because now we have the fluctuating components, the Reynolds stresses, the evildoers, and they include the correlation and the cross-correlation terms, because in turbulence we have the 3 velocity components. And to make things a little more complicated, well, we have a secondary phase. So we write the Navier-Stokes for the liquid and a Navier-Stokes-like equation for the solids. Here we have the presence of the solid stress tensor and the solid's pressure, which are both a function of the fluctuating components in the solids. And we also have the appearance of these interaction terms because, of course, these phases are talking to each other. So this is the data that I need to characterize multi-phase turbulent flows. I need pressures, velocities, both mean and fluctuating for each of the components, and I need information on the concentration. To obtain this data, I use a pilot scale facility at the University of Florida that could flow rates up to 500 gallons per minute. The main characteristic of this setup is that it allowed me to change conditions so that I could have a systematic study of slurry flows. And I'll explain briefly how the system operates, how the experimental technique that I use operates, and then I'll show you some results. The system operates by pumping water from the water tank using a centrifugal pump. The solids are in this vertical pipe over here, at the bottom of which I have a venturi, which is a small reduction and expansion in the area. When the flow passes through the venturi, the velocity increases, the pressure decreases, and basically I suck the particles into the flow. These mixtures of solids and liquids is allowed to equilibrate in 51 pipe diameters before reaching the test section, which is where I collect the velocity profiles. The fact that my test section is located here is important because I wanted to measure steady state properties of the flow. Note that the test section is vertical, and for that it is symmetric, and that is to make it easier to make model comparisons. After I collect my velocity information, oops, I went the other direction, sorry. I need to separate my solids from the liquids, and that is for the sake of the pump. And I do that by gravity. The particles that I'm using are at least 3 times heavier than water. So when they reach the separation units, they drop down into the vertical section again, and water overflows through this mesh area that I have on top. Now, to measure the velocity profiles, I use laser Doppler velocimetry, which is a non-intrusive technique that uses light to measure the velocity of a particle. Many times in experimentation, we introduce a probe into the flow, which might disturb the flow and cause us to measure something else than just the flow itself. And that is not the case with laser Doppler, because the only thing that is going to be passing through the flow is light. The technique combines 2 laser beams into a specific region in space, creating a measuring volume. This measuring volume has the shape of an American football, and when a particle passes through it, it scatters light that has a different frequency than the original beam. This change in frequency is directly related to the velocity of the particle that scattered the light. And so by traversing this measuring volume along the test section, I can measure the velocities and obtain the velocities profiles that I am interested on. Again, since the flow is symmetric, the other half of the profile is a mirror image. And I tested many different conditions, always using water as my fluid and glass or steel particles as my dispersed phase. Particle sizes range from 0.5 to 5 millimeters and concentrations up to 2%. And I changed at different Reynolds numbers, always in the turbulent regime. Today, I want to show you the experiments for the 4 millimeter particles, and I'm going to show you how the velocity profiles in the axial direction change with concentration and with Reynolds numbers. So let me walk you through these results. These are mean velocity profiles. 0 is at the center of the pipe and 1 is at the wall. I am presenting the single phase data at the same Reynolds number in dashed line for comparison in all of these plots. The liquid profile is here to the left-hand side and the solid profile is to the right. So looking at the liquid profile, we can see that in the presence of the particles, the liquid flattens, the profile of the liquid is a little more flattened than in the single phase. Now for the solid, we can see that the relative velocity is decreasing with increasing particle concentration. This is due to an increase in the drag force that propels the particle motion in the streamwise direction. Now let's take a look at the axial fluctuations. Again, liquid to the left, solid to the right. Notice how for the liquid fluctuations, there is a significant increase in fluctuations with increasing concentration. An increase in the number of particles increase the disturbances in the fluids to increase in particle collisions and particle rotation. And this increase in the fluid fluctuations in turn enhances the solid fluctuations that we can also see are increasing with concentration. And we can ask, well, what happens at a different Reynolds number? And this is the comparison. I'm showing to the left-hand side the results at 200,000, which I just discussed with you. And now to the right-hand side, we have the Reynolds at 350,000. Note that at the higher Reynolds, we have a decrease in the relative velocity, which we expected. At the higher velocities, the solids are more easily being dragged by the flow. But note that now the trend in relative velocity has switched. Now we have a relative velocity that is increasing with increasing concentration. And how can we explain that? Let's take a look at the momentum balance for the stationary flow. And I know there's a lot of terms in here, but just stay with me. First, the alpha is the solid volume fraction, the concentration. CD is the drag coefficient, which is proportional to the concentration. So as the concentration increases, the drag increases, and then the relative velocity decreases, which is what we observed for the smaller Reynolds number. But now let's take a look at another two terms, the solid phase stress and the solid pressure, which are both a function of the solid fluctuations, the evildoers in the solid phase. And they both have different signs in the momentum balance. So let's take a look at what the solid fluctuations are doing at the higher Reynolds numbers. And we can see that they are significantly reduced compared to the smaller Reynolds number. And this is because there is an increase in particle collisions that are inelastic and that decreases the fluctuations. And so notice also that the trend has switched from the 200K Reynolds to the 350K. And so this starts to give us a possible explanation of why the trend in the relative velocity switches. So my objective while walking you through this analysis is to show you that different conditions make terms pull in different directions. So some mechanisms might dominate over others. And that is how I would like to summarize this first project. I showed you a gap in knowledge, and you can see that the data that I collected in dark circles started to close this gap. And analyzing this data allows us to start seeing the competing mechanisms and how important data is at the specific conditions, because what dominates at certain velocity might not at a different one, although we are in the turbulent regime. And so let's change gears now, and let me tell you now about my work in fluidization. And for this project, we were interested in studying localized fluidization, which is the situation where the injection into the bed is at a point and not distributed like in the general fluidization configuration. This makes fluidization occur only in a region of the bed. This type of localized flow has applications in chemical industry, in tapered and spouted beds that are used for drying, for mixing, for coating, and many other applications. It has applications in the maintenance of navigable waterway and also sand bypassing operations. And localized fluidization is the cause of the formation of sand boils from underground seepage. This can be an indication of where dams are going to fail, and can also be a problem in chemical industries, as it was witnessed in a chemical accident in Sweden in 2005, where there was an underground pipe that leaked water and caused soil destabilization that made a sulfuric acid tank collapse. Studies on localized fluidization are usually done in shallow beds, which might suffer from wall effects. Another method to study these flows is using direct probing, which may alter the measurements as we discussed in the previous projects. A least intrusive method is to observe the surface of the bed, like in this paper in Physical Reviews, to note when fluidization has occurred, like in just at the surface without introducing a probe. With this method, we don't get any information of how the fluidization was formed. And that is the intersection of what we would like to study in this project. We wanted to study localized fluidization away from walls, finding out what happens in fluidization and defluidization sequences, what is the critical flow rate to achieve fluidization, and how the fluidization is formed. And embedded in all of these points is what is the influence of parameters like the diameter of the injection port, the bed height, the particle roughness, the particle diameter. And today I will just focus on a small portion of this study about the initial stages of fluidization. And we can ask ourselves, well, how can we observe the interior of a granular bed? And I joke that I use magic, but it's really the magic of science. I use a solid that has the same refractive index as the liquid to create a transparent medium. The bed and the liquid in this picture are full of particles. But as I introduce the beaker into the liquid, you can see that it becomes transparent. You can see my fingers behind of the beaker. You can see the writing in the beaker. But the particles that are not immersed in the fluid, they are not transparent. So with this transparent medium, I add a small amount of fluorescent dye into the liquid, and I excite the plane of interest with a laser light. The resulting picture has regions that are dark for the solids because they do not have the dye, and they have a bright regions for the liquid because they have the dye. This picture was taken at the center of the bed. There are about 5 centimeters of particles, which is about 2 inches in front and behind the plane that I'm showing. We place this mixture into our test bed, which is a plexiglass box that has a constant level overflow. And today I will show you only the results for the 3 millimeter particles at 125 millimeters bed height. And I varied the injection port diameter into the bed as I tested the different flow rates. For these experiments studying the formation of fluidization, I would start at a certain flow rate, take a video of the bed for about 5 to 6 minutes, and then I would erase the memory of the bed and start at a higher flow rate. What we observed was that at small flow rates, we are in the static regime. The bed behaves as a porous medium, and it is not deformed. If we start at a higher flow rate, a region of the bed gets fluidized, but does not reach the top. We call this the fluidized cavity regime. At an even higher flow rates, a full localized fluidization is formed. And let me introduce two variables that I will be using to characterize this bed. The first one is the cavity height, HF, which is the height of the moving region measured from the bottom of the bed. The second one is the expansion time T naught, which is the time that it takes for the cavity to grow from the bottom all the way to the top. So if we take a look at the expansion time, which is only defined for the full fluidization regime as a function of the flow rate, what we observe is as the flow rate grows higher, the expansion time grows smaller. As we would expect, this fluidized zone moves faster at a higher flow rate. And let me add the regions in the flow rate where we observe the other two regimes. Blue for the static regime and light blue for the fluidized cavity. Now, these three regimes have been observed in previous studies. And as I mentioned, each of these experiments lasted between 5 to 6 or 7 minutes. And what I noticed during that time is that sometimes this cavity would grow. So we decided to wait longer. And what we found is this new plot to the right. I have kept the original demarcations in the flow rate, and note how everything that I had previously defined as a cavity regime actually grew into a full fluidization, just at a longer time, as you can see by now, this scale being logarithmic and not linear. So we found that the cavity regime is an apparent threshold. The cavity grows slowly, painfully slowly if you want to graduate into a full fluidization. And in light of these new results, we wanted to understand, well, how is a fluidized cavity forming in the white versus the blue regions? And for that, let's pick a flow rate in each of these regions. And if we observe the cavity height, the HF, at the higher flow rate, we see that it's an almost uniform expansion. But at the slower flow rate, we have a very slow initial expansion with a very rapid final expansion at the end. And actually, if we observe the rate of expansion, which is the derivative of the graph that I just showed, we found that the rate of expansion for the lower flow rate is nearly 3 orders of magnitude lower during nearly the entire fluidization process, except again from at the very, very end. One additional distinction for the fluidization in these two regions appears while observing the standard deviation of the expansion time. So here I'm plotting the standard deviation as a function of the flow rate. And notice now how the higher flow rates are a lot more reproducible than the expansion time in the smaller flow rates. And in view of these different kinetics, we can differentiate between the previously observed regular regime expansion and a new ultra slow regime. And the last result that I want to show you is what happens when we change injection port diameters in these two different growing regime regions. And what we notice is, again, I'm plotting here the expansion time as a function of the flow rate. And I'm plotting different injection port diameters from 10 to 40. This dashed line is more or less our demarcation of between this regular regime and the ultra slow regime. And notice that in the regular regime, there is not a big influence on the injection port diameter for the expansion time. But in the ultra slow regime, if we take, for example, 45 cubic centimeters per second, 10 millimeter injection port diameter would expand in about 30 seconds, whereas a 40 millimeter would take about an hour. And we can begin to understand that if we think about the local velocity that is being developed at the same flow rate for different injection port diameters. So to summarize this section, we discovered a new regime where the injection port diameter has an influence in the time it takes for localized fluidization to progress into a full fluidization. So thinking back into one of the problems that I started with, the soil destabilization from a leaking pipe, these findings show that even a small leak can grow a sand boil that can cause problems, and that actually a smaller leak might cause the sand boil to grow even faster if it's subjected to the same flow rate. So I'd like to acknowledge my PhD advisor, Professor Jennifer Curtis, for her guidance and her amazing group throughout the years. I have listed here a world-class group of undergraduates that helped me with experiments, and also Professor Philippe and his group at URSTEA, who hosted me during my stay there. And I would like to wrap up by listing the main contributions of my work. And today I didn't present everything because of time, but just a small fraction. And many details are not included in the talk, but we will have some time to talk right now, and my contact information is at the bottom of the slide as well. But this work resulted in a unique and complete experimental data set for solid liquid flows. I was able to measure the velocity for the solids and the liquids, which is not very common for the 3 velocity components. I also measured pressure drops, granular temperature, kinetic energy, and I did calculations for the turbulence modulation. The way I measured this data using laser-based techniques was a novel combination that provides a new possibility for multi-phase flow experimentation. And the work also shined a light into the formation of localized fluidization. encountering a new regime of expansion, and we develop a model to account for the variables that have an influence on its formation. I continue to be intrigued by what the behavior of turbulent flows will be at higher concentrations and the study of particle shape. And we definitely need more experimental information in both of these areas. And so if you're starting in this area, fear not, there's a lot to study. And conditions matter, and that is why it's important. And that is one of our mottos at my job at PSRI. We are a research and consulting company in particle technology. And we have a wide range of equipment and tools, both experimental and numericals, to study the flow of granular materials at the conditions of interest. And at those conditions, guide the design of equipment. So I get to continue my quest to understand the very interesting world of particle technology. And with that, I would like to thank you for your attention and open up for any questions that you might have.
Outstanding talk, Sarah. Thank you so much.
Thank you.
Outstanding. So, I mean, you don't have the roar of applause like you do have an audience when you're on Zoom, right? But it would be here, no doubt. So,
thank you.
Are there questions from the audience? I guess while people are thinking about it, I can ask one, just being selfish about it. So when you get to higher, in the first part, to really much higher Reynolds numbers, so are you saying that is the turbulence factor and amount of fluctuations of the fluid itself also decreased? So I know you're tracking the particles, and you see that essentially there's dissipation, right? And there's a lot of other ways to decrease turbulence in flows by adding polymers and other things to produce dissipation. So I was wondering if that's really the mechanism here, or is it not a reduction of turbulence?
When I calculate the turbulence statistics, I actually observe an increase in turbulence for all the conditions that I tested. So we really think that in this case, the change, as you say, there are many mechanisms that can be at play. One of the explanations that I gave is really that this is more related to this change in the fluctuations of the solids that we were observing. But again, I am also very curious to see more studies really pulling each of these terms apart and comparing what we get at different conditions. I do not know if I understood your question properly.
No, I'm not sure if I understood my question properly either. So that was a good answer. Anyone from the audience have questions? Mark Olivier, please, you can feel free to unmute.
Hello, Sarah. I want to join Jim, first of all, to really congratulate you. That was extremely engaging, so well presented. Amazing talk. So, you know, both parts of the talk are really interesting. I had one to start with about your transition that you described at the end with these two regimes, right? So, but normally when I think of two regimes, I would imagine there's some type of critical condition. There's a critical velocity. There is just a critical point. Is that something you notice there? Can we really speak about two regimes? Because the curve as it is seems to be one continuous curve. I mean, it's going up very steeply at some point, but what defines really that transition? Yes,
so the transition was, we defined it, and as you said, it is a little, we had to make a decision at some point, but we checked, the standard deviations for sure gave us one of these methods to see what is what. We checked the expansion rate, and we checked, for example, if it had at least these 3 orders of magnitude difference, and the other one was just observing the expansion of the cavity. So these 3 points is what allowed us to draw this line, in this case for the 3mm particles, at about 10 seconds of expansion time. There's where we made the delimitation. but I do not think that that is set in stone. That's a great point. And of course, that changes depending if we had the 5 millimeter particles, it would be at a different one.
Mm.
But our criteria was observing those 3 points. How is the expansion progressing? How is the expansion rate? And how were the standard deviations? Because we did see that it is not as reproducible
Because
for
it's in
the
terms of, yeah, it's in terms of generalizing this, isn't it, for different conditions, right? And to see whether there is some type of critical parameter or set of this
Correct.
that can, almost like a Gelder's plot, right? It might be a zone where there's a transition,
Correct.
and that, of course, be great. I know then your PhD would take even longer, isn't it, for this especially steep, the steep parts. So
yeah,
maybe,
doing replicates on these long experiments, you know.
yeah, the 1,000 seconds there. If Jim allows me to ask something else, is that right?
Yeah.
So at the beginning as well, so when you said there's a compensation of 2 terms, you explained this really well with the Navier-Stokes equations, and you had the drag coefficient in the bottom, and then you had solid stresses, tau s minus ps, and so on. Yeah, that's the one I meant. So what I'm wondering again is what is the order of magnitude of these? So you say indeed correctly, you know, they tend to compensate and so forth, but in what sense? So is there a strong going into one or the other direction? What's determining that?
Yeah, that's a great point. Thank you, Mark Olivier. And you know, I did some calculations when I was looking at these, you know, with the data that I had. But it would be so great to actually see this analysis throughout many values of Reynolds number, and to actually see where, for example, this is uh, where this trend is actually happening, where this switch with increasing concentration, at which point in the Reynolds regime is this going to happen? And so yeah, I do not know the answer to that. I think it will be a very, very interesting analysis. And it truly shines the light at how important the interactions of these factors is, you know, because we could think that, oh, higher Reynolds, and, you know, like it's just higher Reynolds, but not the value in this wide range of Reynolds number has these subtleties that might, as I said, and as you are correctly answering, what is the actual order of magnitude of each of these terms that make things go in these directions. So this analysis was one of the possibilities that we can explain it with. But I am also very curious to see if there are others, and how can we really explain that, you know, we observed this change in the relative velocity behavior.
Seems like there's another PhD thesis in there.
Another PhD thesis, not by me though.
Thank you very much, Sarah. Congrats again.
Oh, thank you, Mark Olivier.
I see Rich has a question. We'll let it, we'll have to probably keep things moving along, knowing time. So go ahead, Rich. Quick question.
Well, maybe just a quick question. Sarah, great talk. Thank you. In both of these cases, though, one of the things that you didn't mention, but I'm sure you considered, was the density of the particles versus the density of the fluid, and the influence of that, which seems to me would make a difference in both situations.
Yes, so your point is that in this case, the density of the particles could be having an effect in the relative velocity. Am I understanding?
That's right. Yes.
Yes, and of course, it would be the case for a different density particle, we would expect to observe a different relative velocity. Now, would we expect to see this trend changing at the same conditions? I do not know about that. But yeah, for sure. And when I spoke about the Stokes number, you know, and the inertia of these particles, the density has, of course, a density difference between the liquid, in this case, or the fluid and the particle, has an effect about how these two phases are interacting and how these two phases are following each other or not. So yeah, the density of the particle has for sure an effect in the Stokes number and how the behavior of the fluid at all happens.
Thank you.
Excellent. Yeah. So just to follow up, the Stokes number is the particle Reynolds number times the density difference itself, right? So as it's defined.
Yeah. So the Stokes number that I used was the density of the particle, the velocities. So yeah, it's as you said.
Yeah. So Reynolds number times exactly the ratio of the density difference, normalized, obviously. So.
Correct.
All right. We do have to move on. Thank you very much, Sarah. That was an outstanding talk.
Thank you
I think
very
we
much.
could ask questions for another hour. I certainly couldn't, but that's not fair to our other speaker and our audience, of course. So
no, thank you. Thank you very much. My contact is there, so if you want to speak more, feel free.